There you go. So here's the deal. We're going to continue on our lesson from yesterday. We're talking about applications of exponential functions. And we're going to learn about 2 extra examples. Yesterday, all we talked about was annual compounding. Annual compounding. But there's other types of compounding as we just listed out. There's daily, monthly, hourly, secondly. And so this formula is just the formula that we learned yesterday tweaked so that you can calculate different types of compounding. And all they did was throw in an n there. An n underneath the r and an n right next to the t, where n is the number of compounds per year. We're good? You get it? So you really have to just memorize one formula and then 2 extra versions of it. This one and one more that I'll present to you. Let's take a look at a real-world problem. Not a real-world problem, but a problem to practice with. All right. So we're good to go. We're going to go through this problem real fast. All you do is use the formula I gave you and apply it to each case. Let's do 1. If things are compounded yearly, that means A is going to be equal to the principal, $1,000, times. If R is 5%, how do you represent that as a decimal? Go. Yeah, it's going to be 1 plus 0.05 divided by, if it's compounded yearly, what's n? Good, because it's 1 year. Divided by 1 raised to the 1 times 1. What's up, buddy? Well, it says after 1 year. It'd be, if it was 2 years, yeah. I don't know about that. T does change. In this particular problem, it's not going to change. But in life in general, for these problems, T will change. T will be different stuff depending upon the problem. And so will n. But for this particular case, right, T is going to hold constant at 1 year, and the n is going to change because it's going to be monthly, quarterly, and daily. Okay. So that's going to be 1.05 to the first. And could somebody calculate that out for me? Let's see. It's going to be 1,000. It's going to be 5% more than 1,000, which is going to be like, what, 1,050. Yeah. 1,050. Let's try and do B. Take about a minute or 2. Let's try and do B. In part B, how is it being compounded? Monthly. And how many months in a year? Good. So if it's compounded monthly, the principal is going to stay the same. We get 1 plus the interest rate was going to be the same, but that's got to be divided now up over 12 months. So 12 is on the bottom. And how many times a year is it going to be built on itself? It's going to be built 12 times, but there's only 1 year we're doing it, so it's going to be 12 times 1. And what I want you to see is that if you manage to get something that compounds on itself more, you're actually going to net a little bit more than if it was just compounding on itself once a year. Does that make sense? You're getting a little extra added built in. So somebody do this for me. What's 0.05 divided by 12? 1.05 divided by 12. Come on, computer. Okay. Let's just make sure. Ay. You know what? I agree. That might be annoying to have to try and write down. And rounding is a pretty bad idea, especially when it comes to exponents, because the amount that you round. So it's hard to write that down. Maybe we could just plug this all into your calculator and have it do all the work. 1,000 times 1 plus 0.05 divided by 12. And we don't have to put extra parentheses around stuff because the order of operations will hold right there. Raised to the, what's 12 times 1? Good. So if you do this, look at that. you get a little something extra that year. You almost get a little bit more than a whole dollar. Point 161898. 161898. So let's do part C, compounded quarterly. It's really great. A quarter is how much of a whole? It's a fourth. So it's compounded 4 times a year, every 3 months or so. But what are you going to put in for n? 4. Yeah. So it's going to be $1,000. 1 plus 0.05, compounded quarterly, 4 times a year. 12 times, not 12 times 4. What am I thinking? It's 4 times 1, right? N times t. Let's see how much this guy is, right? Just going to plug it into our calculator. Now, do you remember I showed you yesterday how to cut and paste using your calculator? Oh, maybe I did that in the other class. Cut and paste, do you know how to take something that you enter in so you don't have to and just recut it to a line? Yeah, second enter, and then you don't have to you can just edit the equation, right? It's going to be a 4. We have to delete that one and raise to the 4th power. Delete that. It's useful. Oh, look at that. 1050.945. 1050. Let's do the last one. What happens when it's compounded daily? No. Compounded daily. Compounded daily, that's 1,000. 1 plus 0.05 divided up all amongst those 365 days, and then it gets multiplied by itself. 365 times 1. Oh, I wonder how big this number is going to be if it is a big number. Let's see. Yeah, I'm going to type it in. It's easier like that. Whoops. Raised to the 365, 1,051.267496. Continuous compounding. It turns out as you start to increase the amount of compounds, you approach a very, very famous irrational number that occurs all the time in nature. Does anybody know what this number is? No? Well, pi is one of them, but there's also another one that's as famous as pi. It's just you don't learn about it until you get really high up at math. Nope. It's symbolized by a little e. Okay? Does everybody know how much e is? Let's take a look. Everybody take out your calculators, and you should see it on there, right? Does anybody see where the e is on your calculator? It's down over here, above the ln. That's e. Let's just raise it to the 1st power right now. E is like 2.71. Happens all the time in nature. It's how sunflowers grow. It's how shells in the ocean for certain creatures grow at this kind of rate. I forgot what the golden ratio is, but I think no. There's not an E. What's up? Okay. In any event, as you start to compound continuously, people found that the number E showed up, and I could prove it to you. Do you guys want me to prove it out? It takes a long time. I'll pass this time for today. What about this? I'll write up the proof. I'll give it to you tomorrow. Yeah. Pert. E equals famous irrational number. Famous irrational number. And then the rest of them you would all know. R stands for rate, T stands for time, P stands for principal. So if you see the vocabulary word in the word problem, continuous. If you see continuous compounding, all you have to do is use this formula. So the tricky part about these, like what we've learned over the past 2 days, is when do you use each one of the 3 formulas? That's what we're going to practice. Here we go. In a state park, the deer population was estimated to be 2,000. So anybody interested in being a scientific researcher or working in science is going to find that they're going to use that formula a bunch. It was estimated to be 2,000 and increasing continuously at a rate of 4% per year. What's the expected deer population in 10 years? So let's do this. Let's do this. Let's figure out how much deer there are going to be in 10 years. Well, we're going to use our new formula because it's increasing continuously. Maybe we actually, you know what, before we just plug into the formula, maybe we should write down what all the things are. What's P? Good. What is R? 0.04. And what's our time period? Oh, okay. Sometimes I do that. It makes problems easier. So now, A is going to be equal to 2,000 times E raised to the 0.04 times 10. I should use a, see, this is where it gets tricky. Yeah, that's what I'm going to do. 0.04 and then 10. You know what? We could probably just plug that into our calculator instead of making it more difficult to write out. Let's do it. Let's minimize this. Let's write it in. Let's do 2,000 times second ln e raised to the 0.04 times 10. Yeah. Yeah, you could also plug in 0.4. There's going to be like 3,000 deer there. That's a lot of deer. 298. Hold on one second. 2983. 0.649. 0.649. You know what? Unless they tell me to round, I'm writing this thing down like this. And that's it.